Hello, everyone. Thank you for joining my talk at the Geometric Analysis Festival. I hope you'll enjoy it. I'd like to thank the coordinators, everyone who organized this conference, for allowing me to join you and to share some of the stuff I've been working on. I hope you enjoy it. Hopefully you caught my introduction, but if not, this slide has all the important information, I guess. Long title, but hopefully by the time we're done, you'll have an idea of what gluing helicoids to make screw-motion invariant minimal surfaces actually means. So strap in, it's going to be fun. So let's first introduce what minimal surfaces are, right? So you may have heard them as the shapes that bubbles will make within a certain wire frame. So there's a few different kinds of ways that we can describe them. So this basic is that they are locally area minimizing. That's the bubbles, right? But maybe the differential geometric perspective is that the mean curvature is 0. So these are surfaces in Euclidean space. Another one is that conformal parametrizations are harmonic. And that's maybe a little less known, but more relevant to the topic at hand, because it connects minimal surfaces to complex analysis in a neat way. So we'll get into that a little bit later. So here are the most basic minimal surfaces. So and they're going to be central to what we're talking about. So the first one is called the catenoid, which is a rotational surface gotten from a catenary curve. And the second is called the helicoid. All right, so helicoid is periodic. Obviously, I'm only showing a portion of both of these. Right, neat thing about these is that they're actually isometric to each other, or catenoids isometric to a portion of the helicoid at least. We'll kind of get into the relevance of that later, right? Yeah. So. Right, so here's a big formula that is not super important, except kind of see like this connection between minimal surfaces and harmonic functions, so that you can basically get a minimal parametrization from what is the real part of a certain complex integral, right? And basically all that comes down to is a function, a meromorphic function, which we call G, and meromorphic one form on a Riemann surface. Okay, the G is called the Gauss map. It's the stereographic projection of the Gauss map, and DH is called the height differential. Kind of the upshot of this is that if you have a Riemann surface and a function in a one form, then you have a minimal surface, right? So it's not as simple as that, of course, because you have no guarantee that it's going to be embedded or like geometrically meaningful in any way, right? So for example, if we go back to the catenoid is basically just a punctured sphere, right? You can see has these two ends. If you were to seal them up, you just get a sphere, right? And for example, if you were to integrate around homology class on the sphere, right, and didn't end up in the same place as you were before, it wouldn't be embedded. So you do need to have the right Weierstrass data and whatnot. So here's some other minimal surfaces that will be relevant to what we're talking about. So this one is called pretty well known. It's called Shirk's saddle tower, or Shirk surface. Right, and some of these minimal surfaces are infinite, of course. So oftentimes the Riemann surface that we look at is going to correspond to a quotient of these surfaces by a certain, in this case, a translation or whatever, a certain transformation to bring it down to a simpler Riemann surface that'll parametrize a fundamental piece of this. So actually, if you do the right quotient for the Shirk surface, you end up with a sphere as well that has 4 punctures. Okay, and this one on the right is called Hoffman-Meeks. okay, or CHM. Okay, so this is another important surface. So not sure if you guys are all familiar with the Costa surface, but that's another pretty well-known minimal surface. So the Kalamata Meeks is like a singly periodic version of the Costa surface. All right. And it turns out both of these are both periodic with respect to a vertical translation. So it turns out that these can be twisted to end up with surfaces that are periodic with respect to screw motion, right? So screw motion is just a translation and a rotation at the same time. We're assuming like translations are technically screw motions, but we're thinking about more interesting ones than that. So screw motion variant minimal surfaces are probably some of the least well-known periodic minimal surfaces. There's not a whole lot of examples, and they're kind of hard to really get a grasp of, partly because if you were to take a quotient, right, the Gauss map wouldn't be it would be multi-valued, right? It depends on which sheet you're in, because it keeps turning every time you go up. All right, so but the most important and the earliest example is the helicoid, right? So hopefully you could tell that one was screw motion invariant. Actually, you could get it's invariant under screw motions of any rotational angle. So it's kind of unique in that way. But another one is a twisted version of Shirk surface. So hopefully you can see similarity between that and this one down here, right? This is just a twisted version. So it was Hermann Karcher who showed that it could be twisted. So we called it a Karcher-Shirk surface. Okay. Another very famous one is, well, the genus 1 helicoid. And then an extension to that is helicoids of any genus, which I don't have a picture for. And another one is a twisted Kalamata-Meeks surface. So these are all basically some screw motion variant surfaces. There are a few others that were known by the turn of the century, but really that was about it until my advisor, Matthias Weber and Martin Freese, developed a technique to get new ones, and that's pretty much what I'm working off of, and kind of generalizing this technique. But really, an important observation to make is that, well, pretty much all of these that we've gotten, that we had images of, if you keep twisting, right, increasing the screw motion parameter, then they eventually degenerate into basically a bunch of helicoidal components. And that's really easy to see with this, with Karcher-Shirk, right? So this is this first one is a little twisted, but basically when you get more twisted, it kind of reaches its limit, and you can see helicoids showing up, right? So hopefully that's clear from these pictures, right? It breaks up into basically two helicoids that are glued to each other, right? So they developed a technique to kind of go backwards from the limit, which I call regeneration, right? Going from a degenerate limit to basically just an embedded minimal surface. And I hope to explain kind of that process to you guys, right? So but to explain that process, I'm going to use first a simpler example, because helicoids are, in my opinion, even though I study them for a living, harder to visualize than catenoids. So we're going to look at the first use of this regeneration technique that Martin Freese used first with catenoids, and that was with the example of another famous periodic minimal surface called Riemann's minimal surface. So this is a really neat minimal surface. Riemann showed it existed, back in the 1800s, and it exists in a one-parameter family. You can see as the parameter changes, that more or less changes the size of these catenoids, right? So Riemann's minimal surface looks a lot like basically planes that are joined together by catenoids, right? And as you push that to the limit, it becomes, the catenoids get smaller and smaller, and so it basically just becomes planes that are just joined together at little points, right? So that's not obviously a minimal surface, but it's the limit, right? These it degenerates to a noted limit, right? So let me explain what that is. So, right, you have, say, if you have a Riemann surface, right? It has different homology classes, right? And if you pinch these homology classes down to just one point, right, you end up with a noted surface. Let's see if I can draw this one. And then, right, it gets pinched down to a point. So that's kind of the basic idea of noted surfaces. So these aren't Riemann surfaces, but they're close, right? And they're limits of Riemann surfaces. And the nice thing about noted surfaces is that they tend to be simpler than than Riemann surfaces, right? The genus kind of gets simplified when you do that. So we'll see how that is useful in terms of getting minimal surfaces. All right, so here's the idea for getting minimal surfaces from regenerating. So let me first give you an idea of maybe what Freese was wanting to do. So he wanted to see if you could get surfaces like Riemann's minimal surface, but with more catenoidal necks, right? So maybe if you could throw in another catenoidal neck. I don't know why. Yeah, catenoidal neck here, something like that, right? Could you have that type of surface with more catenoidal necks? So basically the idea would be to make a Riemann surface that is like what you want and hope that maybe you can get Weierstrass data that works and gives you an embedded minimal surface. So here's the idea. So the idea is you create a Riemann surface from two copies of the complex sphere, right? And you join them together as follows. So here we have two spheres, not going to draw the whole spheres. The idea is at different points, you cut out a disk, right? And so, and then you you identify, maybe give myself a little bit more room. You identify annuli on both sides. Basically, we're going to identify this annulus with this annulus. Okay, so let's think about maybe why that gives us catenoids, or gives us something like catenoids, right? Actually, hold on, let me read this a little bit more. All right, so say we're going to remove points here. Sorry, remove disks. And so we basically end up with annuli. Right, so these are, okay. Give myself a little bit more room. So here we have an annulus. And here we have an annulus. See, we have disks removed. Oops. Good. And hopefully you can see that what happens there is that if you identify these two annuli, you get something that looks a lot like a catenoidal neck, right? It just looks like that. All right, so that's basically how we create this surface that has the catenoidal. This is just a Riemann surface, right? It's no structure on it except complex, of course. That has the necks we want. I should clarify. Riemann's minimal surface is infinite, so again, we're just looking at a quotient by a translation. Okay, so right, so we identify these annuli to get these necks. And so what are the parameters? This is just two spheres that are joined together with necks, right? So what are the parameters that we're looking at? We're looking at, okay, these points where we're getting these necks and the radii of the disks that basically parameterizes the surface. And so those are the parameters that we, or at least some of the parameters that we want to determine, like what they need to be. Okay, so then we can define the Weierstrass data on this surface, and there are different ways depending on what situation you're looking at, but basically the most important way is defining one form, so definitely always do one form, right? And you can do that by fixing periods and residues. So you can define it by using periods around certain homology classes. Like this is a standard homology class that we use to define the one form, right? So, and you define the one form the way that you want it to be, right? So if you're wanting to get catenoidal necks, then, for example, you want, you want the one forms around this to be, to be close, to end up in the same space again. Okay, yeah, and so then, like I said, your Weierstrass data is not necessarily going to give you an embedded surface, right? So you establish what we call period conditions. What do the periods need to be for everything to be closed and to end up with an embedded surface? Okay, so once we've established all that, right? I'm adding a bunch of details, obviously, but once you establish those, then you kind of have an idea of what needs to be true to have the surface you want, okay? But then what, right? We basically have non-explicit one forms and functions on this that we're trying to just integrate and get these closed periods, right? So that's where the noted limit comes into play, right? So these are defined, right, for pretty much whatever values of p and let's see, I didn't say what the radii I call r, right, r sub j. Right, these work for whatever ones, right? But as all of the r's go to 0, right, then you end up with a noted limit, right? So maybe I can just draw that here. Come on. And you basically just end up with two spheres that are joined together at a bunch of points. One of them looks like a sphere, but the other one I'll draw to show that it's noted. Okay. All right, so what happens to the noted limit that's so nice, right? So the catenoidal necks just, they degenerate to just nodes at each of these points, right? And so what happens is the Weierstrass data will converge to much simpler functions and forms, something that we can actually really work with. Sometimes it's actually explicit. But the big important thing is that they converge smoothly. Okay, so that's huge. Again, a lot of math that goes into showing that that's the case, but it is. Right, and so then the period conditions simplify a lot, and we actually just end up with algebraic equations in the parameters, right? Equations usually end up telling you like how the different radii are related to each other as they go to 0. Really, the important the important equations are in terms of the p's, right? So basically we have equations that tell us for what values of these p's we actually get these period conditions solved. So that's still in the noted surface, right? But here's kind of the ansatz of it all is that, well, if to get these functions that you want to be zero, right? Well, if the Jacobian of this set of functions is not singular, then you can use the implicit function theorem to actually get solutions to the period problems near the noted limit, right? So you have these functions that take all of your radii and all of your points, and gives us the periods, right? Again, a lot of detail to it. It's kind of a big picture, right? But basically, you can go from, since the convergence is smooth, like I said, being able to solve it in the noted limit. So solution at the limit gives us solutions near the limit. Using the implicit function theorem, right? So basically this, just really neat idea using a limit that's a lot simpler and then kind of regenerating from it to get to get a one parameter family of solutions. Basically, you can pretty much always express everything in terms of one parameter, and basically get solutions that are what you want. And the other thing is that these algebraic equations, what we call balance equations, will tell us what kind of solutions we can actually have, right? Because they're all going to be near these, right? So you can't just like throw a bunch of canoidal necks and get this surface that's going to be minimal and embedded, right? They have to actually be organized a certain way. Okay, so that's pretty much the idea for this canoidal one. So let me move into helicoidal limits, which is again what I'm working on. But it's really the same thing. So like I said, helicoids and canoids are they're conformally equivalent, right? So that means that all these things you can do with canoids, in principle, maybe they can be done with helicoids as well. So it's a lot easier to visualize canoidal necks and kind of gluing two annuli together to get that, right? But it's actually the same thing, right? In a much harder to see way with helicoids, right? So here's what a helicoidal node would look like. And right, with these surfaces, we're always quotienting by like a translation or a screw motion. In this case, it's screw motion, right? So this like sort of actually gets identified with this, right? And you can see if you just look at this portion, this would be an annulus, right? So it's still an annulus. So you can actually do the same kind of setup by gluing annuli together, just with different Weierstrass data. We'll give you helicoids as well. So hopefully the next picture can kind of give you an idea of how they glue together, right? Basically, this is just two copies of the one above, right? You can see that actually. Right, so here's one copy, and here's another copy. And you can glue them together so that the top portion of one glues to the bottom portion of the second one. All right, so you can still have this gluing of annuli together to get helicoids. Okay, so that's kind of the all I wanted to go into in terms of that. But the idea is you can do the same thing. So there are kind of a lot of other complications, right? For one, when you're quotienting by a screw motion, right? Like I said, the Gauss map is not, it's multi-valued. So you kind of have to go into a lot of other things to simplify that. But basically, you can do the same type of construction and same type of regeneration and end up with screw motion invariant middle surface near a helicoidal limit. Right, so let me at least just present my theorem, right? So here's a picture of near the limits. This is the twisted Kalanoff and Meeks. Near the helicoidal limit. So this one's actually going to degenerate, and you can see it here for helicoids, right? So it's kind of where you see this like heavy twisting going on. And not sure if it's super easy to see based on the picture, but right, maybe you can imagine this, right? Helicoids can go in different directions, right? They can spiral clockwise or spiral counterclockwise, right? So this one is spiraling counterclockwise as it goes up, as is this one. But these two are spiraling clockwise. Okay, so we're dealing with these configurations of points. Where can they be in the limit to actually end up with minimal surfaces and whatnot? We need to attach to each point. So we have these points in the complex plane, and we can attach what we call charges, right? So it's basically plus or minus one that tells us, okay, is it going clockwise or counterclockwise as you go up? Okay. And like I said, if you go to the limit, you end up with equations in the in terms of the points. So here's actually, yeah, so here are the equations that we end up with. So we end up with these functions, right? Fj, which again are just pretty simple algebraic functions in terms of the points, right? So if they're all 0, then you're actually able to regenerate and get a minimal surface near that limit, right? So we say the configuration is balanced if these equations are met, if these functions vanish. And it's non-degenerate, like I said, you need to look at the Jacobian, everything needs to be not singular for you to be able to do that regeneration, right? So in this case, you're going to need to end up with this matrix, which is basically just partial derivatives for all imaginary parts, having rank 2 and minus 1. Okay, so in that case, it's called a non-degenerate configuration. Okay, and so then if both of those conditions are met, then you do have a one-parameter family of screw motion invariant minimal surfaces. Okay, and that parameter is actually going to be the angle of the screw motion, which, yeah, is really nice to visualize, right? So a lot of it's going to have to do with, or what it ends up like is going to have to do with the sum of the charges. So actually, if that sum is 0, then you end up with planar ends. And if that sum is non-zero, then you end up with helicoidal ends. Okay, so yeah, that's kind of the theorem. Basically, if you have a balanced and non-degenerate configuration, then you get a small family, but it's still a one-parameter family of screw motion invariant minimal surfaces near the limit that are embedded and minimal, and they're not noted. Okay, so maybe talk about quickly a few of the types of surfaces that we get from that. So pretty much we get all of the different screw motion invariant minimal surfaces that we have, that we knew of already, right? again, it's still a small family, so it's kind of an open question of like, can we show how much, how big that parameter can get, right? So it's near the limit, it's a very kind of like twisted, strongly helicoidal limit, but kind of just the parameter increases it. Well, I guess it depends, but in lots of cases it untwists, right? So you go from that really twisted Karcher-Shirk to untwist and you get Shirk surface. So that's a topic of interest to me. So this is a twisted version of another surface that I did not mention. It's called Fischer-Koch. That we could twist it using plateau methods, plateau solutions. I don't know if you're familiar with those. We didn't really know what the limit of that was. So this one's actually a pretty interesting one because it limits to two different configurations depending on which way you twist it. So one of them is going to have 3 points, right? And they're all going to have charge negative. But the other limit is going to have 5 points, and it's going to look like a bunch of minuses and a plus in the middle. So it kind of degenerates to helicoidal limits kind of both ways you twist it, which is pretty neat. So this is called Fischer. Oops, did you see there? Cool. Okay. So this is an old surface that basically we're getting back. And plus it looks really cool. But this one is new. So this one is a planar, has planar ends, a planar screw motion invariant. Right, so I think I mentioned that Kalinov and Meeks is planar. And so when you twist Kalinov and Meeks, you're also going to get a planar surface. And the thing I mentioned in my introduction, that was the only planar screw motion invariant minimal surface that we knew of. And so actually are a lot more. They're kind of higher genus and whatnot. Yeah, really, really neat to look at. I really like looking at these and making pictures of them. Okay. And then just a few others that I think are pretty interesting. So this one is like a higher genus Karcher-Shirk. This one actually can't untwist all the way to having these vertical ends like Shirk surface does, but it's still a new surface and aesthetically pleasing. And this one is I don't think I mentioned, but the number of ends that these surfaces are going to have depends on the sum of the charges. Like I think I distinguished between having planar and helicoidal ends, but yeah, some of them will have, some of the helicoidal ones will have more ends if you quotient by a different way. And this is another one that will be asymptotic to a helicoid. So this one's only going to have 2 ends. So a lot of them have more than 2 ends if you like in that quotient. It's only S2. So anyway, these are all, as far as I know, new surfaces, which is really cool. All right, so that's just a few of the examples. I'd love to talk about some others if you're interested. And to kind of close it, another interesting tidbit is connection between these balanced equations and questions in hydrodynamics, especially when it comes to vortices. So it turns out these balanced equations are actually the exact same as some of the ones you end up with when you're studying vortice equilibria. I'm not a physicist, so I don't actually know too much about kind of what all that is, but you do end up with the same equations, right? So these are vortices that are rotating as a rigid body. Right, and so that kind of raises the question, right? What does that mean? Like, why are these related? Is it a coincidence? Are vortices the same thing as helicoids? So I think that's an interesting thing to try to look into. But another nice fact is that this is something physicists have been working on for a few years, right? So they actually have found other solutions to balance equations than the ones that I introduced, some that are a lot less symmetric. And so they, as far as I know, are not interested in the non-degeneracy condition. So not guaranteed that all of these solutions will automatically give you these new minimal surfaces. All the ones that I showed you are also non-degenerate. Yeah, there's kind of just like this wide range of possibilities for motion invariant minimal surfaces that we did not know of. So I don't know. I'm really excited about this topic and the different directions that it can go, and I hope that it's at least somewhat interesting to you guys. So thank you for paying attention and listening, and hope to answer some of your questions when that time comes. All right. Thank you very much.